first, this particular one has a body starting from rest experiences the acceleration. Okay, they may not necessarily underline that, but this is an acceleration versus time curve versus a velocity. But in order to answer the question, you're going to need to create, or that's one way to go about it, create a velocity time diagram from the information that you have here. And what it says, what is the total distance traveled? And this total distance traveled is abbreviated TDT, total distance traveled, and that is versus the word displacement. I can write. Okay, and in this particular case, because the acceleration was all, as we're going to see, a positive acceleration of 1, and then it jumped to 3 meters per second for 1 meter per second for 2 seconds, and then jump to 3 meters per second for another second over this particular 0 to 3 seconds here. And these are the answers over here. The total distance traveled and the displacement for this one is going to be the same, but when you have a situation where you have a reversal, which is going to be what you're going to be looking at here shortly, they're different. If you walk walk from some spot away for 10 feet, stop, turn around, and come back that same 10 feet, then your displacement is 0. You're still where you started from. Okay, the displacement is where you were and where you ended up. Well, if you ended up back at the same place, your displacement 0. Whereas the total distance traveled was you went 10 out and 10 back, so it's 20. Okay, so when you have a reversal, these two are different, but in this particular case, they're going to be the same. So whether they asked you for the total distance traveled or the displacement, you would have gotten the exact same answer. But you get to only see that on a VT diagram. So what I'm going to do is, now remember, you have a nice, very nice actually, pad that they're going to give you. This has a grid, so you're going to be able to do this much easier than I am here, just kind of winging it. So what I'm going to do is put now velocity, and what I've got down here is 1, 2, 3 seconds. Okay, and over here, meters per second. Well, for the first 2 seconds, it's going to go 1 meter per second. So it's going to end up over here. We're going to put, I don't know how I'll do it. Let's see, 1, 2, 3, 4, 5. So 1, 2, 4. And this is in meters per second. And so for 2 seconds, I'm going to go in an acceleration that's going to be 1 to 1. Okay, so this really should be a 45 degree, but again, these two scales don't have to be the same. But I'm going to go this way, and it'll be 1 to 1, 1 foot per second for each second. So you're going to end up to here, and then you're going to be at 2 because you've got 1 meter per second. That's why I like to write this. Think of it as meters per second. So every second we get another 2, so another 1, sorry. So we get a 1 and then another 1, so that gets us to 2 meters per second. But then for 1 second, we're going to go at 3, so we're already at 2, so we're going to end up here at 5. Okay, and this is going to be a 3 to 1 ratio, 3 to each one of the seconds, and you're going to end up here at 5 meters per second. Okay, so this is the VT diagram, and just from integration, the integral is the area under a curve, and so the integral of VDT is the area under this particular curve, and it's all positive, so therefore that's why for this particular problem TDT is equal to the displacement. This is the exact same value here. Okay, so what I can do then is calculate the area. So in this particular case, T dt equals, and I'll abbreviate displacement in this particular case. And so it's going to be equal to this area. So I'll put here, it's a triangle. So I got 1/2 the base, so we've got 2 seconds. And it gets up to the height, which is 2 meters per second. Okay, so that's this area. And then this area here, this is a triangle and a rectangle. So what we have here plus 1 second times 2 meters per second. Okay, so that's this one. So this one goes, if we did this, this would go up to there. This goes to there. And then our last one plus 1/2 the 1 second times the height, which is 3. This height here is 5 minus 2, which is 3 meters per second as its velocity. Okay. So we have is then our t dt, which equals the displacement for this particular problem, is the first one, 1/2 2 times 2 is equal to 2. So that's going to be 2 meters. All these are going to be in meters. So 2 plus, then the second one is going to be 1 times 2, so that'll be another 2. And then the third one is 1 times 1 times 3, half of 3, which is 1.5. So all of those are all meters, and those equal, 5.5 meters, and that is answer C. They could have very well have given you this diagram first, okay? But this acceleration time gives it a little bit extra kick here, okay? But again, all of the area is above the line, and so remember, area above is positive and area below is negative from the, and integration does that for you. But here you're having to do you're doing sort of the integration graphically, because you've got everything is like straight lines. You've got horizontal, you've got constant acceleration, 2 different constant accelerations, and then that gives you linear velocity. If you had linear up here, then you'd have quadratic here, and we couldn't calculate the area under the curve. So this is as hard as it gets. That may be some consolation. Okay. Okay. So you don't like graphics. Okay. Well, let's see if I can convince you that this is going to be easier. Believe me, than what I'm about to do. Okay. If you want to use the equations, that's okay. So we'll use the equations. We'll come back to that. You ain't gonna see me doing it. The graphic approach, man, that just really wins big time. Okay, so what we have is t dt is going to equal again the displacement for this one, whichever one it is. And so what we have is S0 plus V0t plus 1/2 A0 times t squared. Okay, so we want that from 0 to 2, and the reason that's 0 to 2 is because that's what we have, a constant acceleration from 0 to 2 and a constant acceleration from 2 to 3. Okay, but when we get to this point, we have some information based on what we've already done, and that's what you have to keep track of. Okay, so that's 0 to 2 plus S0 plus V0t plus 1/2 A0t squared. Okay, from 2 to 3. You can write it down nice and neat. Okay, so here's our this is our displacement equation. Okay, which we know the position plus the velocities and the accelerations. Accelerations come off the graph from 0 to 2. It is 1, and from 2 to 3 it's 3. Okay, so we know those two numbers. This is 2 seconds, so the t's are going to be 2 seconds. This is going to be, in this equation, the t is going to be 1 second. Okay. But the question is how do you handle these terms after you handle those terms? Well, let's write this out. I think you'll see it better in equation. Okay, so we want to know how far we're going to go. Well, we're starting from some scratch place, so we're starting with 0, and it starts off initially, it says a body starting from rest. Okay, so they tell you it starts from rest, so that's V0 is 0, although it won't be at 2 seconds, so we got another 0, and then plus the 1/2 1 meter per second squared times the 2 seconds. Okay, that's this part right here from 0 to 2. Okay. Now for the second one, we've got S0, but it's no longer 0. It's whatever this is. Okay. I'm sorry, this should be squared. 2 seconds squared. Okay. So 1/2 of 2 squared, well, that's 4. Half of 4 is 2. So what you have here is, and this is second squared, so what you have here is 2 meters. And that 2 meters, you got to remember, that's going to become your S0 for the second term. Not going to be 0, it's going to be 2 meters. You've gone 2 meters. Okay. So you're starting at 2 meters here, and then plus you're going to have a velocity there, and again you've gone 2 seconds at 1 meter per second. So this number here is going to be plus 2, not going to be 0 anymore. It's going to be 2 meters per second times 1 second. Okay, and then plus this term there, well, okay, it's going to be 1/2 3 meters per second squared times 1 second quantity squared. Okay, so this term has already been taken into account here. Okay, so this is really that part. So we end up with is 2 plus 2 times 1 is 2 plus 1/2 3 times 1 squared, which is 1.5. All that's in meters. So you do get the 5.5 meters, which is the answer C. But if you forget and put in here 0 again, if it was 0 up here, even if you picked up the 2, the velocity is now 2, and you lost that 2, you would end up with 2 less than 5.5, which is answer A. Okay, they got you. Okay, they won't get you on the graph because you can see all the areas. You can see you got a triangle, a rectangle, and another triangle. That's what happened here is this is your 2. 1/2 2 times 2 is the 2. So this triangle right here represents the 0 to 2. Okay, that's this 2 meters right here. That's this part right there. Okay, and then the next piece, this one is this term, 2 times 1. Okay, 2 times 1, and then this term right here is this upper triangle. Okay, so each one of the terms in here is a graphic there. Okay, and you're guaranteed that the velocity time diagram, that whatever they gave you an acceleration, would have to be constant accelerations, and you would just have whatever slope that they gave you. And if you constructed that, then the total area under the curve is equal to the total distance traveled and equal to displacement, because all the area is above the T line. Okay, so it's up to player's choice is how do you want to do this here. I want to build your graphical skill though, because I think that's important to see it. I think you see things a lot better